Fractions, decimals, and percents. Three different ways of expressing a portion of something. And on the GRE, you need to be fairly comfortable with moving from one to the other form. So from fraction to decimal form or vice versa. Very common also to have to convert from percents to decimals so that you can use the calculator. And we've talked in a previous segment about, when do you use the calculator and when do you not? We'll touch on that theme a little bit again, as it's not always necessary or even desirable to use the calculator on these questions. You may be better off taking a common sense approach or working on paper. And so our goal for today is to focus on, maintaining good mechanics of solving, as well as using some sanity checks of our answers. It's very easy to make simple errors on these problems because they are so, commonplace. We use percents in real life. I think a lot of people take these for granted. So we'll talk about how to avoid some silly errors and maybe pick up some points on the test. We're also looking ahead a little bit. We'll revisit fractions, decimals, and percents when we talk about data interpretation questions, so laying a little bit of groundwork there. Here's our first problem. We'll work this one together just to kind of get a formula introduced that we'll use in a little bit, or use in the next few problems, and that has to do with percent changes. Or at least percent comparisons, ways of comparing two amounts. It's frequent to look at a percent change in terms of what something used to be and versus what it is now, and look at the percent change that happened in the meantime. This is a comparison between red and blue, and we're given this little chart here. They don't tell us red and blue what. They told us it was red and blue marbles. Well, we could look at this chart and say, well, there's no marking between 6 and 7, but we know it has to be a whole number. So red is at exactly 7. They don't tell us this. This might be teaspoons of frosting, perhaps red frosting and blue frosting, and you can have a partial teaspoon. So we don't know for sure this is exactly at 7, but we're gonna approximate it there, and that's okay because the question itself gives us that option by saying approximately. Okay, so if we need to look at the comparison between red and blue, we need to think about what red and blue are. Blue is straightforward. It comes up to the bar at 2, so blue is 2. But red is stacked on top of that, so we actually have to back the number of blue out of that. So the red bar comes up to 7 as we discussed, but you back out the 2. So red is actually 5. And so the question really is, 5 is approximately what percent greater than 2? And to find a percent difference, always take the difference first before you take the percent. So the difference here is between 5 and 2. Difference is 3. And here the original is blue. So in terms of language, when thinking about what the original is, really here it's not really an original because we're not looking at original versus new. We're looking at red versus blue. So you can look at the words greater than, and whatever follows those are your original. Okay, we're comparing to blue. And so that's what goes in the denominator. 3 over 2 is our fraction. You get a decimal out of that, 1.5, and convert to percent by multiplying by 100. So ultimately 150%. And that kind of makes sense. 5 is 150% greater than blue because 150% of 2 is 3, 5 is 3 greater than 2. All right, here are 2 for you to do on your own. I'm going to give you 2 minutes on the timer for these. right, make sure you've noted your letter answers on your page. And in this first one, we're looking at a decrease from cell 1 to cell 2. That from and to language is a good clue about what's the original and what's the new. If you're going from cell 1, that's your original. And I find that it helps to think about the decrease in absolute terms before I start thinking about decrease in percent terms. So I verbalize it to myself this way. It's a decrease from 50 to 42. That prompts me to say that's a decrease of 8. And half the math is already done once you say that to yourself. Our decrease of 8 is compared to our original of 50. And when you divide that out, multiply by 100, you get 16%. Okay, so A is the answer. And that kind of makes sense, right? It's a relatively small decrease relative to the original value. So an answer like 84 wouldn't make as much sense. And some of those choices up there represent, and I believe 84 represents the percent of cell 1 that cell 2 is. Cell 2, 42, is 84% of cell 1. Okay, so common mistakes just around what numbers you plug in. Second question, total amount of sales in the first quarter. This one's a little different because the percent is given to us. We don't calculate it, but we will calculate with it. We will plug it into our calculation. First quarter accounted for 18% of the sales, and 18% of 1.2 million, the total, is what we're looking for. So good candidate for a calculator application. Go ahead and plug those in. You could put in 1.2 million into your calculator just as is and keep in mind that the result will be in millions. If you're comfortable doing that conversion at the end, you'd get 0.216 million as your answer. And if you are comfortable recognizing that as 216,000, then that's a good way to go. Less zeros to plug in. And in fact, be careful about plugging in zeros in your calculator because notice that the answer choices are all about decimal placement. How many zeros are there? So for that reason, it's worth a sanity check of your answer. Make sure you've picked a number that's in the ballpark. So one way to look at this is that 10% of 1.2 million would be 120,000. 20% then would be 240,000. 18% is what we're looking for, so our number has to be between 120 and 240,000. Probably definitely closer to the higher end there, and so D is the only answer in that range. All right, take 30 seconds on this one. All right, very similar to the last example, only you don't have answer choices to help you or to use as kind of like a sanity check of whether you're in the ballpark. You've got to be correct when it's a fill-in question like this. But in the sense that we have a percent given to us and a total given to us, and we're calculating, the dollar amount of one of these chart segments, it's the same kind of idea. So looking at year 3, that's 7% of the total, and profit total was $612,450 as given. So the big thing to be careful of here is when you put this into your calculator, 7% is 0.07. So you may have to put a 0 in front of a single digit percent before you convert it to a decimal. Remember, you got to move the decimal to the left 2 places and take that percent sign away. So you need another 0 there to move the decimal twice. If you plugged in 0.7 into your calculator, what you really calculated was 70%. So when you do the math in the calculator, you get 42,871.5. They ask for the answer in terms of the nearest dollar. So the rule about rounding is that if you're rounding to the nearest dollar, you look at the 10th place, the first one after the decimal place. And if it's 5, 6, 7, 8, or 9, you round up. If it's 0, 1, 2, 3, or 4, you round down. So this is a 5, we're going to round up. And the correct answer is 42,872. Oh, and by the way, I'm about to talk about this more on the next screen, but I'll mention it here too. You can do a quick sanity check on your answer. 10% of 612,000 would be 61,200. 7% is a little bit, it's close to 2/3 or 3/4 of that. So 3/4 of 60,000 is 45,000. We expect a number kind of in that ballpark. That wouldn't be good enough to get this correct, but it would reveal an error if you had mistakenly calculated that the answer was 428,715. Okay, if you were off by a whole factor of 10, a sanity check would reveal that. All right, so common sense is the name of the game. I heard a rumor that there's a guy who has invented this calculator that will not give you the answer unless you give it, you also enter a guess of what the result should be. And that's the idea here. Think to yourself, what kind of number am I expecting to get out? And by thinking about that before you calculate it, if you get something out of the calculator that is totally off base, you know that you've done something, maybe even as simple as, accidentally hitting a 0 when you shouldn't have. So the thinking goes like this. What percent of 5 is 7? Well, 7's bigger than 5, so the answer should be over 100%. If you look at percent decreases, you can look at, 50% as a benchmark. Clearly, 213, if you cut it in half, you'd be over 100. So a decrease down to 99 is more than half decrease. And benchmarks of 50%, 10%, 25%, anything that's really easy to calculate can be your locating points for what your answer should be. So 0.5% is really hard to envision, but it's easy to calculate 10%. Just take a tenth, and a tenth of that is 1%, and then you can just estimate from there. And going back to the percent change formula, we've already been kind of careful about calculating the difference before we start plugging into the formula, and really careful about thinking about what the original actually is. It's rare for a problem to say, oh, here's the original value, here's the new value, what is it? You won't always see that exact word original. So be on the lookout for language like from 2006 to 2007. What follows the from is your original, 2006 in this oil example. The second one, number of male sophomores in 01, is what percent of the number of female sophomores in 2002. Well, that's kind of a strange question to ask, but it's fair game. Asking about male sophomores in one year, female sophomores in another. What goes in the denominator? When they ask for percent of, what follows the of is what goes in the denominator. Okay, and just calculate as before, set up a fraction, get your decimal once you plug that into the calculator, and then multiply by 100 to turn it into a percent. And looking at two contrasting ways of saying something, it is different to say percent of 8 versus percent greater than 8. When you look at percent greater than 8, it implies that you have to back the 8 out because you want to look at the difference above 8. Okay, so for example, 10 is some percent of 8. We expect that to be bigger than 100 because 10 is greater than 8, so greater than 100%. But when we look at 10, what percent greater than 8, 10 is only 2 greater than 8, and so that's what goes into the numerator. And notice that we would expect those to be different by 100%. They're different by 8. All right, QC question. Very wordy, but I'm going to still give you the regular amount of time. Take a minute 15. All right, talk about real life math. All right. So, still, there's two different stores pricing two different ways, even though it's the same wholesale cost for the coat. And I think the trickiest part of this problem is translating that from English into math. So let's take a look at that. We're told that store M sells the coat initially for $60 more than the wholesale cost. Okay, so that is X plus 60 right here. But then they mark it down and they sell it at a 20% discount. That means they're now selling it for only 80% of what they sold it for before. So 1 minus 20%. And that change happens to that first price they sold it for. So 0.8 times this entire thing. And the thing I want to point out here is that order of operations is critical. They're taking that 20% discount not only on the wholesale cost of the coat, but also on the $60 markup they originally made. Okay, so parentheses are your friends here. Keep using those. Store N followed a different pricing philosophy. They marked it up a certain percent rather than a dollar amount initially. Okay, so they marked it up 60%. That's 1.6 times X. Notice the parentheses. And then they just chopped off $20 from the price. Okay, so it's just a straight up minus 20. And that simplifies this way. And from here, you could start plugging in values, right? We know that X is greater than 90. And we've tested values before. Only do that, though, if you think you're going to be able to prove D. If there's any further algebra that could be done, it's probably better just to clean this up before you start plugging, because there's always that chance that the answer isn't actually D. Okay, so we can clean it up by subtracting 0.8x. We're grouping the variables by doing that. And then by adding 20 to each, we're grouping, a whole numbers in A, nothing but variables in B, and now we can plug to compare. And that lets us plug kind of generally all numbers more than 90. So if X is more than 90, 0.8 of that is always going to be more than 72. And that is definitely greater than 68. We've proven B, sort of by a mixture of algebra and plugging in more than 90 at the end. All right, here's a multiple choice question where you can indicate more than one answer. So think about that. I'll give you 2 minutes here. All right, unfortunately, another true to life example. And I find that's helpful, at least, um, for thinking about how you would calculate the taxes that Mary Ellen paid. The one complicating factor here is that Mary Ellen, we don't know exactly how much money she made. We're given this range. Anywhere between $35,000 and $45,000 inclusive. That means she could have made exactly $45,000 or $35,000. Doesn't mean that 35,001 is the limit at the bottom end. We're also given a range for the tax rate for her. So I find it's helpful just to pretend that we don't have a range for a second and think about just, how you'd calculate that if you had a single number for her salary and a single percent given for her taxes. And it's pretty straightforward to see that if her taxes are a certain percent of her income, we're going to take the percent times her income. And so now we can look at the ranges. Clearly, the lower the tax rate and the lower the income, the less tax she'll pay overall. So the minimum tax that she could have paid uses both the low tax rate and the lowest income. And that sets a lower limit of $87.50. And with that, you can eliminate the first answer. Maximum is just the highest tax rate times the highest income, and that sets an upper limit of $15,750. The bottom answer, the highest answer, is not correct. It's the three in the middle that are possible. And notice that we don't care really, what combination of tax rate and income would lead Mary Ellen to pay $89.92. We don't care about that exactly. What matters is that it's in the range of possibilities. So for percents and ranges in general, looking at the extreme values is the way to go. All right, here is a speed drill. I think this is awfully mean to give you 90 seconds. That's 30 seconds each problem. I'm going to stretch it a little. I'll give you 2 minutes. All right, make sure you have 3 letters written on your paper. And for the first one, it's a QC question with a constraint given, and A mentions variable A, B mentions B. It's best to put those both in terms of the same variable. So you can do that by substitution. I'll show it here as a substitution for A. In quantity A, replace the A with a 3B. And I've written the 50% as a decimal just to make the point that you can do 50 times 3, or in this case 0.5 in decimal form, and get 1.5b. That's equivalent to 150% of b. So A and B are equal here. It's not strictly necessary to put the percent in decimal terms. You could go straight from 50% of A equals 50% of 3B, and it is a valid move to multiply 3 times 50% and conclude that that is 150% of B. Okay, so you could go directly there with percents. Or you could even pick some numbers, right? If B is 2, A is 3 times that, A is 6. And then if you take the percents as indicated by the quantities, you get 3 for both quantities. Now this doesn't really prove C, but if you plugged a couple sets of numbers, pretty soon you would begin to trust that pattern. You can kind of see why you always get the same value for each quantity. Okay. All right, next one, another shopping question. Originally, shirts on sale for $75. Strange store, marking it up instead of marking it down. 17% markup and then a 3% markup after that. Now, if you do a fair amount of shopping, you know this is a retailer's trick. The subsequent discounts. Any second discount is taken off of a smaller amount. Likewise here, the second markup is a markup on a larger amount. So you cannot just add the 2% and say, oh, that's a 20% increase overall. Don't add the percents first. That would be valid if you marked up 17% from $75 and then added another 3% of $75. But the 3% is actually an increase on whatever the intermediate price is. So what you do is multiply by 1.17 and 1.03 for those markups, and you end up at a price slightly over $90. Okay, so A is the answer. Now, if you knew this whole trick about not adding the percents, you might cheat off the easy quantity and say, well, 90% is 20% more than 75. Okay, and what we have is, two markups that seem to add to 20%, but I know that that 3% markup is going to be bigger than 3% of the original. Okay, so A is greater. Just another way to go there. On the last question, we have to actually calculate a percent, and we have this constraint about 2A equaling 3B. Quick word about AB is not equal to 0. All that means is neither A nor B is 0, and in fact, that would be a possibility otherwise. 2A would equal 3B if they were both 0. Okay, so this just tells us that's the one solution that's not possible. Okay, so there's two ways to go here. What we could do is put A in terms of B algebraically, just divide both sides by 2, write it as a decimal, convert to a percent. Okay, there we go, fractions, decimals, and percents all in one question. Or you could pick numbers, right? If A is 6, 2A is 12, so 12 equals 3B, B would be 4. And the question is 6 is what percent of 4? You expect the answer to be more than 100%, and only 1 is here. So you wouldn't even have to calculate that exact percent. Here's a set of fractions. For this, I think I'll give you 345 to think about it. Again, make sure you have 3 answers written on your paper. And the first problem is a fraction manipulation question. So think back to fraction rules previously discussed. Before you flip the bottom to divide by some fraction, you got to combine those terms there. You can't just flip them as is. There's like implied parentheses there. In fact, writing those down on your paper, great thing to do. So to calculate that, go to a common denominator of 20. That's common to 4 and 5. And you end up with 9/20 on the bottom. At that point, you can flip the bottom and multiply with the top. Do some canceling if you want in the middle of that, and you end up at 10/3 is the answer. Or you could even solve this by calculator or check it with the calculator. All of the fractions given in the original problem have pretty easy decimal equivalents, recognizable to many people. So you could actually plug this in. The denominator is 0.45 when you do that, and then just divide that into 1.5, and easily matches up to choice E again. Okay, so 2 ways to go, or at least a second way as a check. The second one here, we've got x is greater than 0. That lets us know that we don't have to worry about some weird cases potentially created by negative numbers. And you may notice the similarity in the structure of quantity A and quantity B. They both have the same number on top and bottom. In A it's 4, in B it's 2. And it turns out that you are able to cancel. So because the denominator is a single term, you can cancel. You can cancel as long as you cancel each term in the top with that denominator. To see that another way, you can think of it as that whole numerator multiplied by a fraction. So in A, that fraction is 1/4. In B, that fraction is 1/2. And the canceling happens. In other words, you distribute that fraction times both parts of the numerator. Okay, canceling the number, and you get the same algebraic expression. So the answer here is C, which means that's always going to be equal, no matter what x you plug in. And that makes this not a very good candidate for plugging numbers in. You might plug in a single value and realize A and B are equal when x is that value, but you haven't proven the always requirement for C. Okay, so algebra is better for proving C. And on this last one, I have a confession to make. The first time I did this question, I did it in such an elegant and beautiful way that it was so disappointing to me that it was completely wrong. I am going to share that with you here because it's possible you did the exact same thing. I saw the similarity again between A and B, and I thought, oh, well, I can exploit that. They're exactly the same except for what the exponent is, x or y. And we know something comparative about those exponents. We know that x is greater than y. And if you just start thinking about just the relative values of x and y, you can sort of extend that to the relative values of each piece of the expressions in quantity A. So what do I mean by that? Well, for example, if the exponent is greater in quantity A, 2 to the x overall is going to be greater. The greater the exponent on 2, the greater the value. And that's true whether you're thinking about positives, negatives, or 0. The greater the exponent, the greater 2 to the x will be. So we don't care necessarily what the value is. Went my reasoning, we can say that part of the expression is greater in A. And what that means is 1 over a greater number, by fraction properties, we know that that piece of the quantity in A is going to be less than the corresponding part of quantity B. Okay, so if we're then looking at the whole denominator, 1 minus something that's less in A is going to be something more in A than in B. Okay, so that whole denominator is greater over in quantity A. And use the fraction properties again, and that would imply that A is less overall. Imagine my surprise when I found a numerical exception to that. It's actually not the case. Okay, so if you picked B, you might have fallen into the same trap I did. It's easier to see what's going on if we look at some numbers. So it turns out that negative exponents are kind of the twist here. So while it's true what I said, that it doesn't matter whether the exponent is negative, 0, or positive, 2 to the x power is greater than 2 to the y power, that is true. But down here, if we had a negative exponent on y, so for example, 2 to the minus 1, that would be 1/2, which would make this whole fraction 2, which makes the denominator of quantity b a negative number. And that shifts the balance, okay? So here we're trying two different cases. X is 2, y is 1. They're both positive. In that case, quantity b is greater. It matches up to the logic I originally employed. But once y is negative, the fact that the denominator gets really negative, or gets negative, means that quantity A can be greater. And so there we go. We've proven D. So there's a kind of an exception there that you don't see unless you plug numbers. Tricky, tricky question. All right, here's another set. This one having to do with powers of 10. I'm going to give you 345 again. All right, jot down your 3-letter answers. Powers of 10, all about decimals, really. I'll share a story. I was an engineer before teaching the GRE, and I started my career at a Japanese automaker. And of course, we use the metric system because it makes a lot of sense. So I was very used to using that and looking at things in terms of millimeters. And, the worst it ever got was 0.5 millimeters, a tolerance or, precision. Maybe 0.1 millimeters, but at least I have a frame of reference for that. I can look at that on a ruler and see approximately what that is. And I left that job and went to work for an American company that makes doorknobs and power tools. And they use imperial units. And so all of a sudden I was looking at things in terms of thousandths of an inch. And that came back to me as I was looking at this problem, this first one. It's all about decimal placement. And it turns out you can do these 0.1 squared, 0.1 to the third power in your calculator, of course. But let's look at the numbers that result. Right? When we look at those powers, what we're really doing is 1/10 is the first power, 1/10 squared is 1/100th, and 1/10 cubed is 1/1000th. And this is where I always kind of got thrown off because, 1,000 has 3 zeros in it, right? But when you're dealing with tenths, hundredths, thousands, there's not 3 zeros between the decimal and the 1. So when you're talking about fractions or decimals, thousands means you put the 1 in the third place. Okay, so there's only 2 zeros. Likewise, hundredths, 1 is in the second place because 100 means 2 places. All right, so that little aside, basically what this tells you then is that there's a 2 in the tenths place, a 3 in the hundredths place, and a 2 in the thousandths place. You could go right to this without further ado. B is the right answer. So looking back, much as, 10 to the third, you can look at that and say, oh, that's thousands because thousands have 3 zeros. Similar here, right? These exponents tell us placement after the decimal. On the second question, it's largely about decimal placement, but also order of operations. Notice that there's a multiply, a subtract, and a multiply. You can't do those just in order from left to right. Remember order of operations, PEMDAS. Parentheses, exponents, multiply, divide, add, and subtract. So multiplying comes before subtracting. Do both of the multiplications first. And parentheses, which always come first, can help you. Just note that on your paper so that you keep the order of operations in mind. Parentheses are your friend. And all that is about decimal placement. So remember, a positive exponent means move to the right. Negative exponent on a 10 means move to the left. So moving to the right 2 places in 0.03 brings us to 3. With 4, you have to put in some zeros before so you can kind of keep track of it, but moving to the left 2 ends us up at 0.04. And subtraction, 2.96 is our answer, and that isn't listed exactly in the answer choices. We have to do some conversion there to see which one matches up. I don't know about you guys. I may be the only one that does the little inchworm, but I find it works, so it's simple. Go with that. E corresponds to 2.96. Last question, QC, has a variable in it, but there's also a lot of cleanup to be done in the number part of that constraint equation. So let's look at that just by itself, left side only. Get rid of those exponents by doing the inchworm and moving your decimal place over so that at least you're in the realm of regular numbers. And you get 5,200 over 13, which divides to 400. And so if the left side there is 400 and the right side is 4 times some power of 10, it means that power of 10 has to be 100. And it's pretty straightforward to see that x equals 2. Another case where a variable isn't really a variable, you can solve for it. The quantities are equal. All right, here's some digits questions. It'll help if you can remember one important shortcut of digits. Good luck. I'll give you a minute 30 here. All right, units digit questions on the GRE typically are about the units digit, or digits questions in general. They most often ask about the units digit, although other digits are fair game, as we see here. But units digit of some power of 2 that is far too large to actually calculate and then just look at the number on the end of it. Instead, the way to go is to exploit the pattern. There's a pattern for the units digit for any number to exponential powers. So what we've written here is the exponential series for 2 to the something. 2, 4, 8, 16, 32, 4, 64, 128, 256. Doesn't seem to be much of a pattern unless you focus in on the units digits. Those repeat in a cycle, 2, 4, 8, 6, 2, 4, 8, 6, and so on. So that's the way we can leap to 2 to the 50th. That's a repeating cycle of 4 terms. So if we look at 2 to the 48, that's 48 is divisible by 4, so that's at the end of a cycle. So 2 to the 49 ends in a 2, 2 to the 50th ends in a 4, just starting up a new cycle. And the answer is C. Very slick. And I should mention that for any single digit, which actually is all that would come into play if you're looking at the units digit, any single digit, if you do these exponential series for them, you'll see a repeating pattern in each of them. The longest one is a 4-term repeat. So very useful property of exponents. All right, the next one is a little bit more complicated because it asks about both the tens and the units digit. And the units digit kind of trick is that, the units digit, when you take a product of 2 numbers, is the units digit of the result is only influenced by the units digit of the 2 numbers that you were multiplying. So in other words, if you were multiplying 81 times 243, if all you cared about was the resulting units digit, you could ignore the 8 in 81, just look at the 1, and you could ignore the 2 and the 4 in 243 and just look at the units digit of 3. 1 times 3 is 3, so that's going to be the units digit of the result. Same property applies if all you care about is the tens and the units. What you can do is just multiply the two terms at the end. So 89 times 46 is going to have the same last 2 digits as the number we would get if we multiplied this whole thing out. Okay, so kind of a shortcut there, smaller calculation. And you get 4,094. Now watch out for a trick. 94 is the 2-digit number at the end of that. Don't pick E, because you're not quite done yet. They ask us not for the two-digit number, but they ask us to do something with x and y individually. So x is the tens digit, that's the 9. Y is the units digit, that's the 4. We take the product of that, and 36 is our answer. Okay, so kind of a sneaky trick at the end. All right, with that units digit principle in mind, this one will become a lot easier. Take 1 minute here. All right, fun problem. You could do in your calculator 23, and then 23 times 23, and then times 23 again, and then times 23 again to see the powers of 23. And, you'd be on the lookout for that units digit pattern. And you'd get there. But a shortcut is that only the 3 affects the answer. So even just looking at the powers of 3, ignoring the 20 part of that base number, would yield the same result. You'd get the same patterns. Only the 3 really affects the answer. The powers of 3 are listed there, enough to get us a picture of what the repeating cycle is, 3, 9, 7, 1. Here the order doesn't really matter. What matters is just that there are 4 units digits possible, 1, 3, 7, and 9, and those are the only answers. Pretty slick. All right, I think this is our last question about terminating decimals. There's a definition of that. I'll throw it out there. There's a rule associated with it. I'll let you kind of think to yourself about what the rule might be, but a terminating decimal is one that ends. So 0.127 is a terminating decimal. It doesn't go on forever. But pi, for example, 3.14159, blah, 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 goes on forever. All right, so with that in mind, take a minute here. All right, so we're asked about the denominator here, and it turns out the rule about a terminating decimal is that a decimal will terminate if, when written as you can write it as a fraction, and the fraction would only have factors of 2 or 5, or both, in the denominator. So some examples. Starting with fractions, 1 over 5 ends up being a terminating decimal, 0.2. 1 over 20 terminates as well. Notice that 20 only is comprised of 2's and a 5. 1 over 1,000 is a terminating decimal. This goes back to kind of the example I was talking about, thousandths of an inch. Here's our 3 zeros in 1,000 and 1 in the third decimal place. So when you think about terminating decimals, 0.127, for example, can be written as 127 thousandths. Since it's 3 places long after the decimal, it's in terms of thousands. And so if you start with a decimal that ends, you can always, if it's a terminating decimal, you can always write it as, the whole number that follows the decimal over some power of 10, just which power would depend on how many places you have after the decimal. Okay, so that power of 10 implies 2s and 5s are all that's allowed. So numbers that don't terminate are fractions with factors other than 2 and 5 in the denominator. So 1 over 6 fails. It has a 2 in the denominator, but that doesn't save it in any way. The 3 is what really ruins this from terminating. It goes on forever. 1 over 7 goes on forever and doesn't necessarily repeat the way 1 over 6 does. Okay, so non-terminating factors other than 2 or 5. And with that rule in mind, answer choice elimination here is a little bit quicker. So some of these answers are going to work no matter what's in the numerator, right? 2, 5, 16, and 25 always would be okay in the denominator here. Because they're comprised of 2s and 5s. And in this case, 3 kind of squeaks by as an exception, but only because there's a 3 on the top that would cancel it out. So if y were 3, k would be equal to a whole number, which of course is kind of a terminating decimal itself, 0.0. All right, and that does bring us to the end. So fractions, decimals, and percents. You can see a lot of everyday math, the percents questions, percent change questions, definitely have some real world applications. Things about terminating decimals, the way those get asked about on the GRE, definitely not a commonplace question outside of the standardized test world. But a few rules really serve as speed techniques on these. So units digit shortcut, kind of benchmarking techniques for verifying your answers, use of the calculator judiciously, all speed techniques, as well as increase your accuracy. So good luck.